Okay, let's dive right into this explainer and explore an absolute engineering marvel. I mean, think about it. Without this tech, massive, bustling cities literally wouldn't exist in unforgiving deserts. The entire internet would probably crash as data servers melted down. Today, we are unlocking the mystery of air conditioning. Stick with me through this because I promise you by the end, you are never going to look at that plastic box on your wall the same way again.
But hey, before we go any further, I want you to really think about what actually happens when you press a button on your thermostat. When the temperature gets totally oppressive and we just expect this magical blast of relief. Ask yourself, does that machine actively manufacture cold air? So here's the crazy part. It is a massive, universal misconception. The reality? Cold isn't a physical entity you can just whip up in a machine. In physics, cold simply does not exist. It's literally just the absence of heat. Therefore, cooling a space is entirely an exercise in moving thermal energy out of it. Now, the most crucial rule of thermodynamics is that heat always moves from hot to cold. If you leave a hot coffee on your desk, it cools down as the heat naturally flows into the room, right? It never, ever happens in reverse. Yet, your AC appears to completely defy the laws of nature. It actually pumps heat backward, snatching it from a cool room and dumping it into a blazing hot backyard. How is that even possible?
Section 1. The Brooklyn Printing Crisis. To figure out this mystery of defying physics, we actually have to rewind to a massive industrial crisis. Because get this, it wasn't initially about human comfort at all. Back in the summer of 1902, a young engineer named Willis Carrier was working for a printing company in Brooklyn. The intense heat and incredibly high humidity were absolutely wreaking havoc on the plant. Paper sheets were absorbing moisture, expanding, and completely ruining the colored ink alignment on thousands of magazine prints. Carrier needed a fix, and he needed it fast.
So, Carrier realizes that blowing air across cold metal pipes filled with chilled water does two things at once. It dropped the temperature, sure, but it also condensed the excess moisture right out of the air, exactly like water droplets forming on a freezing cold soda can on a summer day. This breakthrough completely stabilized the printing process, made the workers way more productive, and, eventually altered global architecture forever. But here's the thing. Plain water wasn't going to be enough to cool down our modern world.
Section 2. The Chemical Lifeblood. You can't just defy physics efficiently using plain water and air. You actually needed a highly specialized secret weapon to act as the courier for all that heat. Modern ACs rely on a chemical compound called a refrigerant. Now, while water boils at 100 degrees Celsius, a refrigerant boils at temperatures well below 0 degrees. That means that even the normal, stagnant air inside your hothouse contains enough thermal energy to boil this stuff instantly.
And wow, the technology has come a long way. Back in the early 1900s, engineers were using lethal gases like ammonia. By the 1930s, the industry shifted to chlorofluorocarbons, or CFCs. You've probably heard of Freon. But when scientists figured out Freon was literally tearing apart the ozone layer, things had to change immediately. Today, we've transitioned to modern, eco-friendly hydrofluorocarbons, or HFCs. They absorb heat powerfully, but without destroying our atmosphere.
Section 3. The four-stage cooling loop. Let's actually look at the mechanical system itself and see how this all builds into a brilliant closed-loop pipeline. This bridges the inside of your home with the outside world using the vapor compression refrigeration cycle. To easily wrap your head around it, just think of it as splitting your house into two distinct zones, a low-pressure side inside that collects heat and a high-pressure side outside that discards it. Let's quickly track the refrigerant through these four exact steps. It all starts at the absolute heart of the system, the compressor. Here, cool, low-pressure vapor gas is violently squeezed into a much, much smaller volume. When you force molecules to collide that rapidly, both the pressure and the temperature spike dramatically. Think about how a bicycle pump gets super hot in your hands when you're inflating a tire. The compressor is doing exactly that, creating a hyperheated gas. Next up, this superheated, high-pressure gas gets pushed right into the outdoor condenser coil. Because the gas in those tubes is now way hotter than the summer air outside, the heat naturally flows out into the environment. A heavy-duty fan blows this accumulated thermal energy away, which actually causes the gas to undergo a phase change, turning it back into a high-pressure liquid. But wait, how do we get it cold again? That brings us to the third stage, the ultimate gatekeeper of the system, the expansion valve. Think of a can of aerosol hairspray. When you press the nozzle, the high-pressure liquid is forced out, and that nozzle feels freezing cold to the touch. The expansion valve works just like that, acting as a highly restrictive bottleneck.
As the liquid forces its way through, the pressure just plummets, causing flash evaporation that instantly chills the liquid down to freezing temperatures.
Finally, this ice-cold, low-pressure mixture enters the evaporator coil, which is hidden inside your home. A blower fan pushes your warm living room air over these freezing copper pipes. The refrigerant absorbs the thermal energy right out of your room, boils completely back into a vapor gas, and travels outside to the compressor, starting the entire cycle all over again. It's genius. But believe it or not, lowering the temperature is really only half the battle.
Section 4. Efficiency and humidity control. Because to make a room feel perfectly crisp, we have to deal with that oppressive, sticky summer feeling. See, high humidity traps heat in our bodies because our sweat simply can't evaporate. But when the warm, humid air in your house hits those freezing evaporator coils we just talked about, it drops below its dew point. This causes the invisible airborne water vapor to condense into actual liquid droplets. And that is exactly why you see those little PVC pipes dripping water outside your house all summer long.
Now, as you can imagine, pushing all this refrigerant and running these massive fans consumes a truly staggering amount of electricity globally. Because of this, engineers meticulously measure performance using something called SEER, which stands for Seasonal Energy Efficiency Ratio. A higher SEER number basically means you've got a far more efficient machine that uses way less grid power to cool the exact same room. So how are modern units achieving these sky-high SEER ratings? Basically, by ditching old single-speed motors for modern variable-frequency inverter drives. Instead of a compressor abruptly kicking on at 100% full blast and then shutting off entirely, which causes massive power surges, inverter technology allows the system to just run continuously at low, highly efficient speeds. It's a total game-changer for maintaining a perfectly steady, comfortable temperature.
Section 5. The Engineering Vocabulary Challenge. Okay. To wrap up this explainer and prove you truly grasp the hidden mechanics around you, let's test that new technical vocabulary.
Throughout our narrative today, we've elevated our language using some really precise, industry-standard terms. We looked at thermodynamic heat conversions, how oppressive humidity totally changes how we feel, how pressure must plummet inside the expansion valve, and how the entire system manages the ambient and stagnant air sitting in our homes.
So here's my challenge to you. Drop a sentence in the comments using at least 2 of these new words. Show off what you learned. But before you go, I want to leave you with this ultimate thermodynamic paradox to chew on. As our world continues to warm, the global demand for this physics-defying technology is skyrocketing, which demands more and more power from our electrical grids. Are we cooling our homes today at the expense of heating our planet tomorrow? Think about it. Thank you so much for joining me for this explainer. Stay curious, and I'll see you in the next one.